Good afternoon, sir. Good afternoon, sir. Uh, Dr. Agrawal, are you able to hear us? आप उनको अनम्यूट कर दें। Sir, your voice is not coming.
नहीं, अभी नहीं बोल रहा हूँ, अभी आप कहेंगे तब शुरू करूंगा। हाँ ठीक है, आप बताइए कितने दिन में शुरू करना है। ठीक है, ठीक है, ठीक है, ठीक है।
Okay. Good afternoon, sir. So we are going to start with the session today. That's the third day of FDP. So I will ask Ankita ma'am to just introduce the sir.
Good afternoon, everyone. Today's third session will be with Dr. Sanat Agrawal. Dr. Sanat Agrawal has done his graduation in mechanical engineering of UP, India. He obtained his Master of Engineering in 1990 with honors from University of Roorkee, India, IIT Roorkee, in mechanical engineering. He served as a foreign guest researcher at National Institute of Standards and Technology, Maryland, USA. He worked there on generating an information model for the representation of heterogeneous material data based on 1003 steps. He was a postdoctoral fellow at the Central University of Technology at Bloemfontein. His areas of interest are CAD and additive manufacturing. He has several years of experience in CAD and AM area. Served as a faculty member in the Mechanical Engineering Department at JUET Guna during July 2009 and May 2018. He served there as Mechanical Engineering Department during May 2014 and June 2017. He joined NIT Uttarakhand as an associate professor in the Mechanical Engineering Department in 2018. He has supervised 7 MTech students and 2 PhD scholars so far. He is currently supervising one PhD scholar. He was the head of the mechanical engineering department from December 2020 to January 2022. He's serving as the Dean RNC from February 2022 onwards. Dr. Agrawal OPI of ICMR New Delhi funded project on fabrication and testing of lower limb prostheses for transtibial amputee using biocomposites with energy restoring capability with a total outlay of rupees 7 lakhs. Dr. Agrawal has published several has published various research in national and international journals. He has also published a book. He is a reviewer of reputed journals like Computer Aided Design, Rapid Prototyping Journal, World Journal of Engineering and International Production Research. He is also a reviewer of South African Journal of Engineering and RAPDAS conference proceedings. He is a regular member of SME, a member of ASME, and RAPDASA, Rapid Product Development Association of South Africa. He is also a life member of ISTE. Welcome, sir. Welcome to our FDP. We are very privileged and happy to have you here with us. Please share your knowledge with our participants. Thank you, sir.
Thank you very much for the introduction. Very good afternoon to all the participants. This afternoon, we will speak on the topic 3D printing of polymers. I will start with the introduction, organization of this presentation. I will talk of types of polymer printing. What are the different types of polymer printing based on the machine architecture and material transformation physics. So I have classified under 5 categories, as you can see: photopolymerization processes, powder bed fusion processes, extrusion based processes, printing processes, and sheet lamination process. So I have categorized under these 5 categories types of polymer printing, and I will discuss them. This classification is based on the machine architecture and material transformation physics. The first classification is photopolymerization process. Here there are sub-classification: vector scan or point-wise processes, mass projection or layer-wise processes, and then third one is two photon process. So the first category, as I said, is photopolymerization process. Here there is a polymer which is irradiated with ultraviolet light or visible light or some other kind of radiation, and the polymer is the material is polymerized. So it is polymerized because of the radiation, so that's why it is photopolymerization. There are 3 categories, subcategories: vector scan and mass projection or layer-wise processes, and two photon process. The first subcategory, vector scan, is point-wise. Okay, point-wise means there is a scanning laser beam. There is a small laser beam, scanning laser beam, which is performing the vector scanning. And second one is mass projection or layer-wise. In the second process, the complete layer is fabricated at one go. So there is a mask which is formed and the mask is projected. So this is layer-wise processes. And there is a third category which is called two photon processes, 2PSL. Here there is a research work going on. This is also a point-by-point fabrication, but there is a difference with the vector scan because this is taking place in 3 dimensions. I will discuss with photograph. As I start discussing photopolymerization process, I will discuss these 3 with figure. Then it will be, you will be able to distinguish. And in the second category, powder bed fusion process, there are different types of PBF or powder bed fusion processes from different companies. For example, there is a SLS process from 3D Systems Inc. There is a laser sintering process from a German company called EOS GmbH. These machines are called EOSint machines. Okay. For polymer printing or plastic printing, it is P series, eosine P series. The third category is extrusion-based process. There is a machine, FDM machine from Starter Stitching, fused deposition molding machine. This is very popular. Most of you who have done 3D printing or printed part must have printed from this machine. This is quite an affordable machine. Machines are available from 10,000 to 1 lakh, 2 lakh. These are affordable machines, but if you go some high-end machine to 30 lakh, 40 lakh, it goes in that range. But these are widely used in the industry as well as in academia. These are extrusion-based processes. The FDM machine, the name of one company is Status Inc. Status is Inc. They started this machine. The first patent, they had patented this machine around 1992. When we go to the third classification, that we will discuss. Then there are printing processes. There is an indirect printing and direct printing. Indirect printing, the bulk of the part material is not printed, but the binder is printed. So this is also called binder printing. And then you have direct printing when the bulk of the part material is printed. Like photopolymer, if it is a liquid polymer, it is printed. Liquid material is there. It is printed from the inkjet head, and then it is polymerized by ultraviolet radiation. So there are two types of printing process. Printing process, as I said, something is being printed with the inkjet head. Either the binder is printed, binder which is not the bulk of the part material, or the bulk of the part material is printed. So this is different from the first two, photopolymerization process and extrusion-based process. Photopolymerization we can classified as vector scan, MPSL, and 2-photon. And extrusion-based, the material, there is a extruder head. From the extruder head, the material is extruded. So in that way, printing processes are different from the first two processes. And then the fifth category that we will study is sheet lamination process. In the sheet lamination process, there is a supply roll and there is a sheet of roll. There is a roll of sheet, and the roll of sheet is, there is a supply roll and there is a take-up roll. From the supply roll, the sheet is supplied to the take-up roll. In between, it is cut and glued to the previous layer. So when we can go to the fifth process, that we will discuss. So among the sheet lamination process, there is a LOM process by Cubic Technologies. There is a plastic sheet lamination PLS, PSL, called Solido 3D from Solid Dimension. There is an Envision LD 3D modeler from 3D Systems. And binder printing, there is a process whose name is 3D printing. 3D printing is a generic name also. 3D printing is also used for additive manufacturing. You know, this FDP is on additive manufacturing or 3D printing. So there are several monikers for this technology. 3D printing, rapid prototyping, additive manufacturing, desktop modeling, model making, time compression technology. There are several monikers. The same technology is known by several different names. Okay. But ASTM standardized it and they called it additive manufacturing technology. So all the technologies which are additive in nature and it is done layer by layer, all those technologies are clubbed in this umbrella term, additive manufacturing process. Okay, so 3D printing is one of the moniker. So 3D printing is generic name also, but in the fourth category, when we say 3D printing, we refer to this binder printing. Okay, so as we will see, this was developed by MIT. And then there are several direct printing processes. For example, T66 and these are two models from SolidScape, T66 and T612. And then object from Starter Stitching and PolyJet printers from 3D Systems. So we will study in this lecture today, we will study 3D printing and object, connects, etc. So we'll start with the first category, photopolymerization type of AM process that use polymers. So I'm discussing in this lecture today, I'm discussing 3D printing of polymers or additive manufacturing where the raw material is a polymer. Where the material is a polymer. a monomer is there which is polymerized in the process. So in the first category, photopolymerization type of AM process that use polymers, there are three configurations for photopolymerization in a vat: vector scan, mask position, and two photon approaches. These three configurations we will show in a figure, in the next figure, so that you will be able to appreciate it much. So first one is vector scan or point-wise approach. This is also called vector scan SL. Vector scan stereolithography, the abbreviation for stereolithography is SL. So this process is also known as vector scan SL. So this is typical of commercial stereolithographic machine find commercially. Most of them will have vector scan stereolithography, or they will have point-wise approach. There will be a scanning laser beam. The scanning laser beam will be scanning on the resin surface. Second one is mask projection or layer-wise approach, MPSL. It is called MPSL, mask projection stereolithography. This is a layer-wise approach because a mask is used and it masks the area where light should not fall, and rest of the area light or radiation goes through and the material is polymerized. So the whole layer is polymerized at a time using this approach. And there is a two photon approach. So this figure, if you have any query anytime, you can interrupt me and ask. So you see this figure. This is a schematic diagram of three approaches to photopolymerization process. The first category is photopolymerization process, and the three subclasses are vector scan, MPSL, and two photon. These three subcategories of photopolymerization process are shown here. The first one you see, this is vector scan SL. I said there is a scanning laser beam which scans. So you see, or this is a point-wise approach. So you see, there is a point which is irradiated. In this approach, there is a point on the resin surface which is irradiated, and a point is solidified or photopolymerized. So in this process, there is a vat of resin, vat of acrylate, liquid acrylate or epoxy resin. Resin can be of two types in the SL process. Either it can be acrylate or epoxy. Initially, they started with acrylate. So this is a vat of resin on which a part is built. There is a platform. This is a laser ray. This is a laser which emits a laser beam, and there is an optics. Here there is an optics, and there is a XY galvanometer or scanning galvanometer. So using the optics and XY galvanometer, the laser beam is deflected on the resin surface. You see, this is a vat of resin, and this is a resin surface. And this is the platform on which the part is fabricated. First platform is just one layer below the resin surface. So initially, the first layer or the bottommost layer is fabricated. Okay. So the laser beam scans the resin surface. Wherever it has to be photopolymerized, that region is scanned. So wherever the laser beam scans, the region is solidified or photopolymerized, and the rest of the region is not photopolymerized. So if there is an overhanging area, for example, this area, you may need support. If the slope is too much, can you see the arrow? You can see the arrow. So this slant area, if the slant is too much, then you may need to provide a support, because there is a liquid resin adjacent to this solid area, and you cannot form it if you do not have support. So there is a support required in this process, and support has to be built along with the part material. And this is second one is mask position SL, the second figure that you see, it is mass position SL. Here there is a large radiation beam. There is a laser or lamp, UV lamp or laser, and from the laser it goes to the optics. From the optics, you obtain a large laser beam. That large laser beam is deflected by the DMD mirror. There is a DMD here. There is DMD stands for digital micromirror device. There is a this is a raster scanning. There is an array of mirrors, and the mirrors which are on, only those deflect the beam, and in that manner we'll discuss it in detail, but I am just making a passing remark. Only those mirrors which deflect, they solidify it. Corresponding region is solidified. So this is as you see, this is a mass projection SL, and so the complete, you see here there is only a single laser beam. Here after irradiation, it is irradiating the whole layer, and so the whole layer is fabricated in one go. And you see this is two photon approach. In the two photon approach, there are two laser beam, two scanning laser beam, and wherever they intersect, the reaction takes place there, and that region is solidified. So this is taking place in 3 dimensions. Vector scan SL is taking place in 2 dimensions, only on the resin surface. Only the material on the resin surface is solidified. In the two photon approach, it is 3 dimensions. It is like holography, similar to holography you can imagine. So this point is solidified. Then in the similar way, you scan from the bottom up. You start from the bottom up. You scan the bottommost layer, then you scan the second layer. But here there is no platform which is moving. So these approaches, all these 3 approaches, there are 3 approaches shown here to photopolymerization. These are bottom-up approach. First, the platform is just one layer below the resin surface, and the bottommost layer is fabricated. First, you fabricate the bottommost layer. Then the platform goes down. Then the second layer from the bottom is fabricated. Then the third layer. So this is bottom-up approach. You start from the bottom. First, you fabricate the bottommost layer. Then you go upwards, and the top layer is fabricated at the end. I will also show a process which is a top-down approach, where there is a system called perfectly that we will study later. In that process, the topmost layer is fabricated first, and then to go down. So that is a top-down approach. So there are 3 configurations: vector scan or point-wise approach, mass projection or layer-wise approach, and then 2-photon approach. In the vector scan SL, there is a vat of polymer, as I said, and there is a UV radiation from laser which scans the resin surface. There is a scanning laser, and UV radiation comes out of the laser scanning laser which scans the resin surface. Platform is lowered after one layer is scanned, and then another layer of resin is recoated above the previously formed layer, and part is thus grown layer by layer. We'll discuss this process in detail. First, small introduction. Then mass projection SL. It utilizes a large radiation beam that is patterned by, so DMD, digital micromirror device, is used for patterning the beam. As I said, there is a digital micromirror device. There is a array of mirrors, and the mirrors are either on or off. Those mirrors which are on, they only deflect the beam. So it is patterning the mirror. The large radiation beam is there. It is patterning the large radiation beam. Only some beams, some of them are deflected, others are not deflected. So in that way, it is patterning the beam. Then third one is 2-photon SL, 2P SL. As I said, photopolymerization occurs at the intersection of 2 laser beam. In the first process, vector scan SL and MPSL, there is a need for recoating. But in 2-photon SL, there is no need for recoating. Here there is no platform. Here there is a platform MPSL and vector scan SL. There is a platform. The platform goes down once a layer is solidified or photopolymerized. The platform goes down, and then the resin covers the previous layer, and there is a recoater blade which recoats. In the 2-photon SL, there is no platform. Resin is not at all disturbed. There is no resin delivery system. There is no recoater, so recoating is not required. So, but however, this process is under research, and this will come out to be more accurate. So this process, 2-photon SL, 2P SL is faster and less complicated. Okay, we will discuss in more detail vector scan SL process. So the first process, the first subcategory of the first category photopolymerization process is vector scan SL or vector scan stereothography. Among the stereothography processes, SLA, stereothography apparatus, SLA from 3D systems is the most representative system. There is a company called 3D Systems. It is a very large company. It not only makes SLA process, it produces and markets several other processes. I can say that this is the largest company. It is based on California, as far as I remember. And the SLA process, stereothography apparatus process from 3D system is the most representative SL process, stereothography apparatus, stereothography process. The 3D system, the stereothography product line from the 3D system consists of Project 6000 HD, Project 7000 HD, ProX 800, ProX 950 as production machines. So these are the product line which are a little older. So new product line has also come up. And the layer thickness in SL process, this ranges from 0.05 mm to 0.15 mm. So laser thickness is of the order of 0.1 mm, 1/10 of an mm. Some processes which are very accurate, it will have a layer thickness up to 0.05 mm. Where there is no slanting surface, no curved surface, you would like to have layer thickness larger so that the 3D printing process is fast. So you can go up to 0.15 mm. Okay, so suppose there is a slanted surface, or there is a curved surface. So for accuracy, you would like to go for lower layer thickness. If the layer thickness is lower, then on the slanted surface or on the curved surface, there is a staircase effect which appears. This is the inherent accuracy. You can imagine this is a layer by layer process. So once a layer is built, the walls are vertical. Second, on top of that, second layer is built, the walls are again vertical. So if there is a slanted surface, there are steps. So that kind of step effect, staircase defect occurs. So if the layer thickness is too small, if you keep the layer thickness small, that staircase defect that decreases and accuracy increases. And laser beam spot size that ranges from 0.13 to 0.76 mm. So the machine accuracy in stereothography process, it is of the order of NC machines. It is very accurate. Machine accuracy is very accurate. Part accuracy is plus minus 0.127 mm or better. And surface finish for up-facing surfaces, surface finish is in the range of sub-micron RA, average surface roughness value. And for slanted surface, it is above 100 microns RA. RA is average surface roughness value. And these have, when you use the material for SL, so they have moderate mechanical properties. So this is a better schematic diagram for SL process. You see, there is a laser from which UV radiation is emitted, and there is a galvanometer-driven mirror which scans the resin surface. This is a vat of resin, vat of liquid acrylate or epoxy resin, and there is a platform. The part building is taking place on the platform. And first, the platform is just one layer below. So the first layer that you see here, that layer was first fabricated. You are in, say, 30th layer. The 30th layer is being fabricated. After that, the 31st layer from the bottommost layer will be fabricated. So in that way, the part is grown layer by layer, bottom up. So there you can see there are two lasers. First laser is here, second laser is here. So this laser is emitting UV radiation for part fabrication. There is another laser, helium neon laser. This layer is used to measure the level of the resin. So level of the resin should be maintained at a particular level. If the level of the resin, because part is being fabricated, shrinkage may take place, or due to recoating, the resin may be displaced. So so that every time the layer thickness is same or at the desired level, the level of the liquid should also be maintained. That is maintained by helium neon laser, which is falling here and it is being sensed. It senses the liquid level. Okay, and this laser, the first laser is for part fabrication, which is emitting the UV radiation. So previous SL systems, the initial SLA stereotherapy apparatus systems from 3D system, they were using helium cadmium laser. But the current SLA system, they are using solid state laser, that is NDYV04, neodymium yttrium vanadium oxygen laser, NDYV04 laser, which is a solid state laser, more stable. These are more stable laser. They are using this one. So I said the SLA process, stereotherapy apparatus process, is the most representative system from 3D systems. So 3D systems, I will give you some chronology of the 3D systems. 3D systems was founded in 1986. So, and the process is SLA, stereotherapy apparatus. That process, SLA, stereotherapy apparatus, was patented in 1986 by Charles W. Hull of UVP, Ultraviolet Products, California. And the company 3D Systems Inc. was founded by Charles W. Hull and Raymond S. Freed in 1986 in South Carolina, SC, South Carolina, USA. This company, 3D Systems Inc., they manufacture the SLA systems. They acquired the SL business of US GmbH in 1987, and they also acquired DTM Corp. Laser sintering systems in 2001. The laser sintering systems from DTM Corp. In 2001. So you see, I said SLA Systems is a very large company. It is listed in NASDAQ, and they not only they are producing and marketing the stereotherapy apparatus SLA process, they are also marketing several other systems. Like they are also marketing the SL of USGM. They acquired the SL business of USGM in 1997. They are also marketing that system and some other systems like laser sintering systems of DTM Corp. Okay, and the first machine that was commercialized by 3D Systems was SL1 in 1988. Okay, the machine was called SL1 in 1988. And then there came an SLA 250. The model name of the machine model was SLA 250 that was announced a year later in 1989. So why 250? Why it was SL1? Because it was the first machine, and SLA 250 because the build volume was 250 by 250 by 250 mm. Its length, width, and height was 250 mm. So from there, its name came SLA 250. They have SLA 250, SLA 500. Now they have different models, as I had explained to you. Okay, so this is the SL process, stereotherapy process, SLA stereotherapy apparatus system from 3D Systems. I discussed chronology. And then when the part is fabricated, there is a weave pattern used. Initially, they used the weave scan pattern. The different kinds of scan pattern being used in the SL processes, these are called SL scan patterns, stereography scan pattern. The first one is called weave scan pattern. Then there came star weave scan pattern. Then there is a SS, accurate clear epoxy solid. The third one is SS, accurate clear epoxy solid. That one is not only the scan pattern, but the build style. It encompasses the build style, parameter, etc. So initially they used the scan pattern they used was weave scan pattern. In the weave scan pattern, you see this is one layer. You look at the figure below. I think you can see the cursor. Yes, you can still see the cursor. If you have any query anytime, you are free to ask me. So if you see figure 4, figure 3, 4, 5, let us call it figure 5. If you see the bottommost figure, so this is the weave pattern, this is the star weave pattern. So this is one layer, this is the second layer. So second layer, the scanning is done on top of the first layer. Okay. And for each layer, there is a scanning is done in the X direction and Y direction. Okay. But in the second layer, the scanning is done on top of the first layer. So, but you see, this is independent, this portion is independent. The second layer, it is not interlinking, there's no cross link with the previous layer. But here in the star weave, you see the second layer is staggered. It solidifies the previous layer also. So star is the abbreviation, star is an abbreviation, star weave scan pattern. The first term star is the abbreviation for staggered alternating sequence and retracted hatch pattern. So it is staggered, first layer and second layer, they're staggered so that first layer solidifies photopolymerizes with the previous layer also. And alternating sequence, there are 8 scan sequence used for, and there is one sequence consists of 8 scan sequence, and this is alternated. This add scan sequence first this add scan sequence was done, then this is repeated. So in that manner, so that is alternating hatch pattern, alternating sequence, and then retracted hatch pattern. So this was for the first scan pattern. Weave was good, but still there were some drawbacks. There was some distortion. To reduce the distortion, they improved upon it, and the star weave scan pattern. This development was taking place in the 90s. And the hatch pattern is retracted. You see, this is one pattern, this is another pattern. So this pattern is retracted from the border. This is the border. So this pattern doesn't touch the border. This hatch line doesn't touch this border. So this allows distortion. Distortion and shrinkage takes place. So this allows distortion, shrinkage, and this reduces the shrinkage and curl. And then third one, as I said, third scan pattern is SS, accurate clear epoxy solid. So that was the different scan patterns: star weave, and SS, SS for accurate clear epoxy solid. So then we will discuss the second subcategory of photopolymerization process, which is mass projection SL process. So as I said, mass projection SL, mass projection stereography technology, or MPSL. Here, whole layer is fabricated at one go. So there is a mask which is created, and some of the radiation is masked, and the radiation is allowed to go to the region where it should be solidified. So therefore, in this process, one layer is fabricated at a time. So you can imagine, if you compare it with the previous process, vector scan SL, where for fabricating a layer, there is a scanning laser beam, and it is fabricating from point to point. It is scanning from point to point. How fast MPSL is, you can imagine. So here, it projects a raster image on the resin surface. Raster image means there's a raster where the points are on and off. Wherever it is on, light goes through and it solidifies that point. So it cures a complete layer at a time. It is much faster than the vector scan SL. And in this process, they use DMDs. What are DMDs? DMDs are digital micrometer devices as their dynamic mask. This process, as I have told earlier also, they use digital micrometer devices, DMDs, as their dynamic mask. And the radiation source for such systems is UV lamp. The UV radiation reflects from the on micrometers onto the resin surface to cure a layer. There are two machine models that I can name, which uses this MPSL technology. One is Perfectly from EnvisionTech. Another one is V-Flash from 3D Systems. So 3D Systems is no more producing V-Flash, but Envision Perfectly from EnvisionTech is very popular. EnvisionTech is the name of the company, and Perfectly is the name of the process from EnvisionTech. So this is the schematic diagram of the MPSL mass projection stereography from Georgia Tech. And you can see in the lower figure, they have a photograph also of the process. So as we have seen, I had shown a figure where there are three processes combined, similar to this one, but this is particular to Georgia Tech. So there is a broadband UV lamp, and UV lamp, you see it falls on the, there is a large UV lamp, large ultraviolet radiation, which is falling on the digital micrometer device. And digital micrometer device, there are on mirrors. There is a array of mirrors, and the mirrors are either on or off. Whichever mirror is on, that reflect the light on the screen. And how much angle it has to be reflected, that is calculated by the software. So that corresponding point on the resin surface is photopolymerized or solidified. So you see, there's a large UV radiation which is deflected by the laser beam, and the whole layer is photopolymerized at one go. There's some optics here, and there is a DMD, digital micrometer device. The photograph of the same, there is a UV lamp here, and there is optics here. You see this optics corresponds to the optics here. DMD here. There is a lens here. There's imaging lens. This imaging lens is here, and the laser ray is reflected from the DMD on the resin surface. So again, here also, bottommost layer is first fabricated, and the part is fabricated layer by layer, bottom up. So this is also called that the part is grown, because it is being fabricated layer by layer. So these are two models from EnvisionTech. This figure is taken from Gibson in the book by Gibson et al. 2010. I'll give you the full reference of the book. This is a Perfectly model from EnvisionTech. Then this model is P4K, perfectly P4K model from EnvisionTech. This figure I have taken from their website, EnvisionTech, P4K. And let me start. So this perfectly process from EnvisionTech is very similar to Georgia Tech machine. It uses a UV lamp and there is a DMD, digital micrometer device. What is the difference between the MPSL and perfectly? MPSL, as I said, it is bottom-up approach. The bottommost part is first built, and then second layer, third layer, and finally the topmost part is built. Here, this is the top. One major distinction is part is being fabricated below the platform. I will show you how. In the MPSL or vector scan SL, part is being fabricated on the platform. So bottommost layer is first fabricated, and then second, third layer goes on being fabricated. And here the part is being fabricated. Here you see, here the platform is here, and just try to imagine the platform is here, and platform just there is a single layer. So that layer is irradiated from below. So that first layer is fabricated, and then the platform goes up, and then next platform is here and part is being fabricated below that. So first the topmost portion, layer is fabricated, then the second layer, third layer, and last at the end bottommost layer is fabricated. So this is the top-down approach in contrast to the bottom-up approaches in vector scan and MPSL. I hope I am clear. If you have any query, you can ask me. So here platform is here. Platform is just one layer below the this surface. There is a container, and this is the side. This is a side surface. The cylindrical container is there. That top lid of the container and bottom lid of the container. So the platform is just one layer above the bottom lid of the container. Okay, and it is irradiated. This portion is there. Inside there is a UV radiation from below. It is being irradiated, and bottommost layer is fabricated. Then second layer, third layer onwards. I hope you caught it. So in this process, VAT is eliminated from bottom in contrast to vector scan and MPSL, where there is a laser ray from top and part is fabricated on the platform. Here, part is fabricated below the platform. So build platform is raised, resin fills the region due to gravity, and advantages in this process. You remember in 2-photon SL process, recorder is not needed. Here also, recorder mechanism is not needed because resin fills the region due to gravity. And the window on the bottom, there is a window from which the UV light is radiated. That window is flat, so there is a precise layers being built. So when the platform is raised, small features may get damaged. So that is the disadvantage of this process, that small features may get damaged when the platform is raised. So the third process is 2-photon SL process. Here there are, in the vector scan SL process, there is a scanning laser, there is a single scanning laser. Here there are two scanning lasers. You can see this is one scanning laser, this is second scanning laser. And these are driven by, this will be computerized, and the orientation will be given by software, so that they intersect, both of the laser intersect at the point where it is desired. Okay, and here photopolymerization in the 2PSL process, photopolymerization takes place where the two beams from the two scanning laser intersect. Okay, I think it is clear to everybody. So the photopolymerization in this process occurs at the intersection of the two laser beam. there is no need for recoating. The part is fabricated below the resin surface. Okay, in this process, perfectly I said there is no need for recoating. Here also there is no need for recoating. It is like holography. You can imagine this research work is going on in this process. You can imagine if we make a hologram inside the liquid resin, inside the a material like acrylate and epoxy resin, if we make a hologram, it may solidify. So if you make a hologram, we have a layer by layer process. Here the whole 3D object will be solidified immediately. So that is the next stage of research work. Two photon approach is being extended in 3 dimension, and people are also trying to make a hologram kind of thing where the complete 3D object will be solidified in one go. So within within a span of minutes, the whole object will be fabricated. So there is no need for recoating. You don't disturb the resin surface. Okay, in the previous one, the platform is lowered and the resin covers the previous layer. And then there is a recoating, resizing is required so that there is a plane level. It is leveled. Here there is no need. This process is much faster and less complicated. In this process, feature size of 0.2 microns is equal to 0.0002 mm. So such smaller feature size has been achieved. So you can make parts, you can go to making parts of which are of mm order, millimeter order, and which has features of in the order of microns. That kind of smaller parts you can fabricate using 2 photon SL. There is another vector scan micro SL where also you can fabricate smaller parts, but 2 photon SL is also used. So this process is under research, as I said, and the extension of this can be using a hologram. If you have any query, you can ask anytime. So first category we have completed, photopolymerization processes. That was important. I put more emphasis so that it is clear to you. So in the first process, there was a liquid material, liquid resin such as acrylate or liquid acrylate or liquid epoxy, which was there is a radiation, UV radiation or visible light radiation or any other type of radiation which falls on it, and it photopolymerizes and it becomes a solid. Okay, so the first category was that process. We will go to the other processes. The second category is powder bed fusion type processes that use polymers. So we use polymers, polymer material such as plastics, but this is powder bed fusion. So we'll discuss how this this kind of process takes place. The SLS process, selective laser sintering, is the most representative process in this category. SLS process from 3D systems. DTM core was sold to 3D systems, so now this is being marketed by 3D systems. And EOSint, the EOS company, German company, EOS GmbH, they also market the SLS process called EOSint P machines. So as I said, the SLS process from 3D systems is the most representative SLS process or powder bed fusion process. In the SLS process, solid state sintering takes place. Those of you who have expertise in material, they know sintering can be of different types. Solid state sintering, liquid state sintering. So this is here, low temperature is used, like 70 watt CO2 laser, 50 watt CO2 laser, that kind of laser is used. And these are low temperature lasers, and solid state sintering takes place. The material is heated to a temperature 10 to 15% below the melting point. So bonding takes place because of high temperature, and the material is heated as well as compacted. One layer of the material is deposited, one layer of powder is deposited, and it is subjected to high heat from the laser, as well as before it is being subjected to high heat, it is compacted. There is a recoater blade which moves and it compacts the powder. Recoater blade or roller mechanism is there. Two kinds of recoating mechanism is there: roller mechanism, and there is a recoater blade. So when the recoater blade moves, it compacts the powder also. So it is subjected to high heat as well as pressure. Because of high heat and pressure, heat below the melting point, so it doesn't liquefy, bonding takes place. So that is solid state sintering. So solid state sintering of polymers takes place, and polymer materials such as nylon 12, polyamide is used. So I have given you example of material which is used in this process. Polyamide is used. Polyamide is nothing but nylon 12. So PA12 is one proprietary material that is used, is eosynth machine. I said there are machines from 3D system which are called SLS machines. There are machines from US German company US GmbH which are called eosynth P machines. For plastic material, eosynth P series is there. Okay, so in the eosynth P series, there are several kinds of proprietary material that can be used. One of them is PA12. Then they have composite materials, so they name it differently. Composite material may contain the nylon as well as some metal powder. Metal powder is not solidified, only it is bonded with the plastic. Okay, or some flame retardant material is used, so accordingly the name of the material is done. So these kind of materials are used in this process. Let us look at the sketch of the SLS process. First, try to understand the process, then we will go to chronology and discussing the process in detail. So I said a low temperature laser is used. Like I said, 70 watt CO2 laser. Eosynth P395 machine, P398 machine, they use 70 watt CO2 laser. If it is for metallic machines, which is not the topic today, if you are using a metallic powder, then 5 kilowatt, 5000 watt laser can be used. But here, only a 70 watt CO2 laser is used. So laser power is small, so the temperature is low. Okay, and that's how you don't liquefy the material. This is a solid state sintering. You keep it below the melting point. Okay, so there is a CO2 laser. From the CO2 laser beam emanates. Radiation comes out from this, and there is a galvanometer-driven mirror or XY scanning mirrors from which the laser beam is deflected on the powder bed. So this is the powder bed. These are two supply bins or feed cartridges from which powder is fed. So this left-hand side is a powder feed cartridge or powder bed. Right-hand side is again a powder bed. And middle one is where part fabrication is taking place. So this is called build platform or powder bed. So the laser is deflected from the galvanometer-driven mirrors, and it scans the surface of the powder bed in a manner similar to SL process. In the vector scan process, the laser was scanning the resin surface. Here it is scanning the powder bed. So it is selectively scanning the powder bed. It is scanning only those portions which has to be solidified. For example, suppose it starts from this point, it will not scan here, it will start scanning from here and end here. Then it will go to the next line and it will not scan here, it will scan here to here. It will, again, it will scan to here to here. It will scan for this line, it will scan from here to here. In that manner, it will scan and solidify this layer. And the layer is, as I said, of the order of 0.1 mm. Okay, 0.1 mm, 0.8 mm, that is the typical layer thickness in the process. Some of the processes go up to 0.05 mm also. So let us look at the chronology, then we'll come to the detail. So SL, the stereography apparatus by Charles W. Earl, this was patented in 1986. And he formed a company in 1986 itself. First machine was commercialized in 1988. You will see around the same time different technologies were evolved. 1986 SLA, 1988 you will find SLS, FDM also you will find 1988, 1992. So around the same time most of the processes were developed. 3D printing process by MIT around 1994. So 80s and 90s in the previous century, most of the processes were patented and commercialized. But they were, in the initial stage, they were called rapid prototyping machines. They were particularly used for product development. They were not used for making an end-use part. They were only being used for product development. So this process, SLS process, it was developed and patented by Mr. Carl Decker at the University of Texas at Austin in 1986. Carl Decker was a PhD student at the University of Texas at Austin. He, along with his supervisor, he got this topic from his supervisor and he developed the SLS process in 1986. They founded the company DTM Corp in 1987. And they commercialized the SLS system in 1992 called SLS Interstation 2000. As I told you earlier, this SLS technology, the complete company, it was acquired by 3D Systems Inc., South Carolina, USA in 2001. 3D Systems Inc., South Carolina, USA, they acquired complete company, the whole company DTM Corp in 2001. So they started manufacturing the SLS system and marketing it. So apart from 3D Systems, there is another company, as I told you, EOS GmbH, which started, which manufactures this technology, and they call it EOSynth P machines. They started their SLS venture in 1989, and they introduced its first EOSynth P machine in 1994. I worked as a postdoctoral fellow in Central University of Technology in South Africa. They had this machine. The company, I was there in 2004 to 2006. The German company EOS GmbH, they had gifted them one machine. So they had this machine. Then I was working in JP University of Engineering and Technology, JUT Guna. We had acquired that machine, EOSynth P395. We had acquired that machine that was installed in 2012. So that machine is around 2.5 crore. Quite a costly machine, but very sophisticated machine, and parts are quite accurate. So apart from 3D Systems, another company, German company is there, EOS GmbH, which is producing the SLS machines. So in this process, SLS process, it is we are in powder bed forming process, is a powder-based process. Here, it makes a model or prototype by sintering the powder. We have a powder bed on which powder is supplied from the powder feed cartridge on the powder bed. One layer is deposited, and then this layer is sintered using a COT laser. Okay, a thin layer of powder is deposited, and bottommost slice is selectively drawn on the powder bed And once the laser falls on it, the powder particles are sintered and form a solid mass. I told you it is a solid state sintering, and uh, uh, it is a solid state sintering, and some kind of bonding. I told you that some kind of bonding takes place. It is not melting and solidifying. It is not below the melting point. It is not above the melting point. It is below the melting point, 10 to 15% below the melting point. So particles are sintered and form a solid mass. So once one layer is formed, powder sintering bed is lowered, another layer of powder is deposited, and the laser scans the next slice, and the part is thus built layer by layer. So this is the SLS process. Okay, so this is the powder bed where the powder sintering takes place. Once a layer is solidified, the powder bed goes down, the build platform goes down by a layer. Next layer of powder is deposited by this roller mechanism. This is the recorder mechanism. This is the recorder mechanism. This can be a recorder blade or a roller mechanism. Two kinds of recorder mechanisms are used. Either a recorder blade is a Zephyr blade, or a roller mechanism. What it does, it takes the powder from feed cartridge and deposits here and levels it and removes the extra powder beyond the powder bed. So this leveler, in one go, it does first, it goes from here to here and deposits the powder. Second time, it goes from this powder feed mechanism. Okay. So two categories of polymer printing we have covered. First one was photopolymerization. Second was SLS, powder bed fusion process. Third one is sheet lamination type AM process that uses polymers. So here, in this process, the material available to the system is in the sheet form. I told you there is a sheet which is going from the supply roll to the take-up roll. Sheet can be, in this lecture we are discussing only polymer, but sheet can be paper sheet. In the same process you can use paper sheet, you can use aluminum foil, but you can also use polymer sheet, plastic sheet. You see the figure is here. So there is a supply roll, there is a take-up roll, there is a sheet on the supply roll. From the supply roll it goes to the take-up roll. So sheet is moving from the supply roll to the take-up roll, and once a layer is made, once you fabricate a layer, you cut it, and then there's a heated roller which presses it, and the second layer is glued to the previous layer. So in this process, cutting takes place. Laser used for cutting. Though this is an additive process, a layer is added on top of the other layer, but here laser is not used for photopolymerization or for sintering. Here the laser is used for cutting. So you see there is a CO2 laser, there is a optics, X-ray positioning device, and here in this process the laser beam is always vertical. It is cutting the sheet always vertically. Whereas in vector scan, MPSL, or in the SLS process, the laser beam is reflected and forms an angle other than 90 degree with the powder bed. But here it is always vertical. So there is a laser which cuts the outer contour and inner contour, and the rest of material has to be removed. So rest of the material, to facilitate the removal of the extra material, small pieces. So that is why, and it is cut, but it stays there. It acts as a support of the part material. So there is a sheet of material. The under surface of the sheet has a glue material. So once the second layer comes on top of the first layer, it is glued to the previous layer. So in this process, gluing or adhesion bonding takes place. The laminate is bonded to the substrate, then cut according to the slice contour. In the long process, laminated object manufacturing by cubic technologies, it uses a CO2 laser to cut. So the company is not manufacturing the long machines; they were only repairing. So this is obsolete system, but this is an important process to understand with this sketch, because a lot of new machines have come up which utilizes similar technology. They use a very small sheet of plastic. The long process, then second one is Solido 3D by Solid Dimensions. The name of the company is Solid Dimension and technology is Solido 3D. The same technology is also being sold by 3D systems called Envision LD 3D Modeler. They utilize an XY plotter, as I told you, XY plotter, which scans in the XY direction for cutting the PVC sheet and for writing with anti-glue pens, which inhibits bonding. The support material is the support material. I told you there is a part material, outer contour, inner contour. So outside of outer contour is acts as a support material. That support material is subdivided into small region for ease of removal. I told you they are cut into small pieces for facilitating the removal. The support material, if you don't cut it in small pieces, how will you remove? You will damage the part material. So that is cut in small pieces using the laser itself. So the company Solid Dimensions, they closed their business in 2001. So additive manufacturing, which was previously called rapid prototyping, this is a rapidly developing technology also. The technology is developing rapidly. Many of the processes are becoming obsolete, and many of the good processes, practical processes are coming up based on the previous process. So this is not only a rapid product development process, rapid prototyping process, this is also rapidly changing process. So this is the sheet lamination manufacturing, the third category, sheet lamination type. The sheet I told you, it can be a plastic sheet, cellophane paper, or it can be a paper, or it can be an aluminum sheet. The third category was sheet lamination. First category was photopolymerization. Second category was powder bed fusion. Third category was sheet lamination. Fourth, we are coming to extrusion type AM processes that use polymers. The additive manufacturing process that use polymers, but the material is extruded. There is the extruder head. The most representative examples under this category is the FDM process by Stratasys Limited. There is a machine by Stratasys Limited which is called fused deposition manufacturing. Fused deposition modeling. FDM is the abbreviation for fused deposition modeling. The material is fused and deposited layer by layer. Okay. And these are the material used. I will show you the figure. First, I will explain the process. Then I will go other things. Let me give you the chronology. So I told you the processes were developed around the same time. SLA was 1986, patented was 1986, and SLS I told you 1988, around 1988. So the extrusion-based processes which use polymers, for example, FDM, that was also developed around the same time in 1988 by a gentleman called Scott Crum. Scott Crum developed it in 1988, and he was awarded a US patent in 1992, and he formed a company called Stratasys Limited. Stratasys Limited commercialized the FDM system in 1992. The first FDM machine that came to India was FDM 1650. FDM 1650, I was doing PhD from IIT Kanpur, and we did our PhD work in that machine. So that machine came around 1996. So in 1996, the machine came and installed. So that is, I have also given you a chronology of machines in India. First, two machines came in India in 1996. First one is in IIT Kanpur, another one was IIC Bangalore. IIC Bangalore, or there is a CSIR lab in Bangalore. I think that that CSIR lab it came. So the two machines came in 1996. So you see, 1992 it was commercialized. It came to India very soon. Within 4 years, it came to India. And this was the first AM machine that came to India. First additive manufacturing machine that came to India. So there is a spool of filament. In this process, you see there is a spool of filament. Filament, in this process, filament is used. Okay. Filament such as ABSA, polyphenol sulfone, one of these materials, filament of one of these materials is used. And the filament, there is a spool on which filament is there, and the filament is fed from the spool to the extruder head. It goes to the extruder head. In the extruder head, there is a liquefier. In the liquefier, the filament liquefies, and it is viscous. There is a viscous paste which is formed. It is not liquid. It doesn't have very low viscosity. It is quite viscous, and so a viscous. That's if it is not viscous, then it will flow from the extruder head. If it is very liquid, then it will flow from the extruder head. But we need to extrude it so that we can form the part layer by layer. So we make here a viscous paste is made, and viscous paste is extruded from the extruder head. This is the extruder head. Actually, only one tip is shown for part material. Actually, in the extruder head, and some advanced machines, some second level machines, there in the extruder there are two tips, one for the part material and the other one for the support material. Okay, so why two tips? Why the other tip for support material? Because you see here, unlike the SLS process or unlike the LOM process, where the unused material acts as the support, here there's no unused material around the part. This is the part which is being built. If there is a slanted surface or curved surface, you will need a support. In the SLS process, which is a powder-based process, powder-bed fusion process, the unused powder remains there. For each layer, the unused powder remains there. We don't remove unused powder layer by layer. It remains there. So unused powder acts as support for the overhanging features. Here, there is no such kind of support. So here, whenever you have to, there is a overhanging feature, you need to build a support. So there are two tips in the extruder head. One is for the part material, and the other one is the support material. And this part, here you see the prototype part which is being built. It is built layer by layer. In this figure, you see on the right hand side, bottom right portion, you see the process has been explained. From the extruder head, there is a nozzle tip. From the nozzle tip, the material is extruded. A viscous paste is being extruded, and it is extruded layer by layer, and the part is grown layer by layer. So this is a sketch. Actual mechanism will differ from machine to machine, but this is a schematic diagram. So in the extrusion type AM process, the FDM process, fused deposition modeling from Stratasys Limited, is the most representative process. FDM process is the most representative. Many companies use. Actually, the patent from Stratasys Limited expired. They patented around 92. You see the chronology. They patented in 1992. They got the patent in 1992. So it expired in 2012. After 20 years, around 2012, it is expired, and people were free to manufacture the machine. But still, they have a lot of patented technology in that. They keep doing research and patent some other technologies. But the process came out of the patent, and there were a lot of manufacturers. They started making FDM machines, and affordable machines are available in 20,000, say 1 lakh. You will get only, if you buy a 1 lakh machine, you will get only extruded head with only one tip for the part material. You will not get support material. If you want support material also, then you will have to go 2 lakh, 4 lakh machines. And if you want good accuracy, then you have to go to 30 lakh, 40 lakh machines. So materials that can be used in the process are ABS. ABS is acrylonitrile butadiene styrene, which is a tough plastic. ABS-I is high impact ABS, ABS plus, and then there is a material ABS blended with PC. PC is polycarbonate. Okay, then there are polycarbonate material available. PCISO is for medical purpose. PPSF is polyphenol sulfone. Then there is another proprietary material, RTAM 8085, 9085, which is a flame retardant material. So I told you that viscous paste should be made. So polymers that are amorphous in nature can be extruded in a viscous paste rather than in a lower viscosity form. So polymers that are amorphous in nature are preferred compared to highly crystalline polymers. Highly crystalline polymers are suitable for powder bed fusion process such as SLS process. Here are some of the properties of the FDM material. So the last final category is the fifth category, which is printing type AM process. When I was classifying in the beginning, I said printing type AM processes, there are two types, direct printing and indirect printing. Direct printing, the bulk of the part material is printed, and indirect printing, the bulk of the part material is not printed, but the binder is printed. You know, when you are making a part using additive manufacturing, you are using the printing process, there is a bulk of the part material, for example, powder, which is printed. Powder forms the bulk of the part material. How is powder bonded? There's a binder which is used. Binder bonds it. So binder is not the bulk of the part material. The powder which is used is the bulk of the part material. So when you print the bulk of the part material, it is direct printing. When you print the binder, it is indirect printing or binder printing. The first category is binder printing or indirect printing. The most representative system is 3D printing developed by MIT, and it is being marketed by 3D Systems. For direct printing, the processes are T66 and T612 from SolidScape, Object and Connex from Stratasys, and Project Printers from 3D Systems. So we'll discuss the binder printing. You see, this is the binder printing process. In the binder printing process is indirect printing, so binder is printed. And powder is not printed from the inkjet printhead. Powder is deposited. You see, this is the powder bed, and this is the powder delivery system. There is a roller which takes the powder from the powder delivery system and deposits on top of the powder bed. So one layer of powder is deposited. On top of it, binder is selectively printed so that the layer solidifies. Okay. In SLS process, there is no binder. In the SLS process, it is solidified using the laser. But here, in this process, there is a binder is used which binds it. Okay, that is the difference. So this process was invented at MIT and patented by Dr. Emmanuel Sachs in 1989, and they have licensed to more than 5 companies. It prints a binder, and binder droplets are 80 micron size. They form spherical agglomerates. Once a layer is solidified, the powder bed is lowered, as in the SLS process, and the new layer of powder is deposited on top of the solidified layer. And the process of printing and recoating is repeated. In that manner, the part is grown layer by layer. So here also you see the unused powder remains in the bed. So that acts as a support. Just like in the SLS process, the powder is sintered and unused powder remains in the bed. So unused powder acts as support to that layer and the layer that will come above that. So even if there is a slant, you don't need to build support. For example, here you see This is an overhanging feature. But there is no support needed. The unused powder which is lying below, that acts as the support. So parts are supported by unused. These are the advantages. Parts are supported by the unused powder. And in the powder bed, you can perform 3D nesting. You can make some part here, then you can make some part here, then you can make some part above that, you can make some part here. In 3 dimensions, you can nest the part. That you cannot do in the SLA process. In the powder-based processes, you can do it. Like in the SLS process, you can do it in 3D printing. These 2 processes you can do which are powder-based processes, but you cannot do in FDM process. 3D nesting you cannot do in FDM process. 3D nesting you cannot do in SLA process. So that is the advantage. And you can make the complete assembly using this process. Assemblies and kinematic joints can be fabricated. So now we will come to direct printing. The previous one was binder printing, which was not direct printing, it was indirect printing because the bulk of the part material was not printed. In the direct printing, as I said, the bulk of the part material, the part material which forms the bulk of the part, that is printed. Okay, so that is direct printing. So I have given 3 examples. The models, the machine model T66 and T612 from SolidScape. Okay, second one is object from Statasys, and third one is Connex from Statasys Limited. These are the 3 machine models where I have listed here. So in SolidScape T66 and T612, these machines employed 2 single jets. In the machines T66 and T612 from SolidScape, they employed 2 single jets, one to deposit a thermoplastic part material and another one to deposit a waxy support material. So from one jet, part material is deposited, from the another jet, support material is deposited. The part material is thermoplastic, support material need not be strong so that you can break it away. So that is a waxy, that is a wax kind of support material. Okay, and in this process is melting and solidification based. There is no UV radiation. This is not solidified using UV radiation like vector scan SL or MPSL. This is not solidified using UV radiation. Or in SLS process, powder bed fusion process, SLS process I discussed, it was solid state sintering take place using the laser. But here in SolidScape's T66 and T612, there's no UV radiation. Melting takes place, the material is melted, and then it solidifies to form the layer. Application of it is the part that you fabricate can be used as patterns for investment casting. Then the other process is object from Statasys. Statasys Limited has 2 processes, object OBJET. This is this acronym has been formed by jetting. An object is formed by jetting. Jets are used for forming an object. So that the name of the model is OBJET object. Another one is Connex. So in the object process from Statasys Limited, there are multiple nozzles used in the printhead. There are 512 into 3 nozzles. 512 into 3 is 1536, and 512 is 2 to the power 8. So 3 into 2 to the power 8 nozzles are used in the printhead. Okay. So these 1536 nozzles, they form a line. So this is line-wise printing compared to point-wise printing in vector scan and layer-wise printing in MPSL, mass projection SL process. This is a line-wise printing. Okay, so this process is line-wise printing. As I told you, there is a rapid line-wise deposition efficiency is achieved in the object process. And the material uses acrylate material. And acrylate material, you remember in the vector scan and MPSL, I told you that two kinds of liquid resins are used: acrylic resin and epoxy resin. So this is very similar to vector scan, only the certification process is quite different, little different. Okay, quite different. So here also acrylic material is used and it is cured by ultraviolet radiation. So you see, this is this is a direct printing process. And direct printing was 3D printing, which was developed by MIT, where the binder was printed. And one direct printing process I am showing you in the figure. Here, the bulk of the part metal is printed. What is the bulk of the part metal? Bulk of the part metal is a monomer which is photopolymerized. The monomer is printed, and there is an ultraviolet light which is irradiated on the bed, and it photopolymerizes or solidifies. So as I told you, it is a line-wise printing, and there are 1536 jets. 1536 jets. 3 into 512 is 1536 jets. So there is a line of jets. In total there are 1536 jets from which the monomer is printed. And you see, this is the jetting head. It moves in the XY direction. The jetting head can move in the XY direction. It moves in the X direction along this rod, and there is a Y axis. And this is the build tray. Build tray moves in the Z axis. And here you see, unlike the powder-based processes or sheet lamination process where the unused material acts as support, here unused material cannot act as support because this is a liquid. It cannot act as support, so it has to be solidified. So wherever there is a support material, full cure S is the support material and full cure M is the model material. So from the printed, either the support material is printed or the support material is printed. Selectively printed. Wherever part material is to be printed, part material is printed from those jets, and from the rest of the jets, the support material is printed. And they are solidified by the same ultraviolet light. You see two shadows here. This is one shadow and this is another shadow. So this region is, there's an ultraviolet beam, ultraviolet radiation in this region. In this rectangular region, there's ultraviolet radiation that along with the extruder head, along with the line of the jets, the rectangular region of ultraviolet radiation also moves, and it solidifies the polymer. The monomer which is printed from the inkjet, it solidifies. So in that manner, the photopolymer is formed, and that line is solidified. That line moves along the x-axis. This is the x-axis. That line moves along the x-axis, and in that manner, a layer is formed. So this is faster than the vector scan, but slower than MPSL, mass projection SL system. And you can easily understand the difference between vector scan and this process, object for object process, and 3D printing process, which was patented by MIT. In 3D printing process, the binder is printed. Here, the bulk of the part metal is printed and solidified. Here, there is no binder, only part metal which is printed, and it is solidified using the ultraviolet light. And these are the bibliography. Those interested, this Gibson, Rosen and Stucker, this is the good book. And Kua is also a very old book available in the market. They have a 5th edition. There are several other books you can refer. This is another book by Jan Gibson for medical application. There's a book on rapid tooling also. So those interested can refer to the book. So these are 5 ways you can use a monomer and print it. So 3D printing of polymers can take place in one of the 5 ways. I have discussed all those 5 ways. Photopolymerization based, sheet lamination, direct printing, indirect printing, powder bed fusion process. These are the processes which can use a monomer and solidify it, make a polymer. So that concludes my lecture. If you have any query, you can ask.
Thanks a lot, sir, for your valuable session. Any query from the online participants? Please ask. It's a very informative session. Please raise your hand or put your query in the chat box. Anyone?
I was having sore throat, so my voice was a little hoarse. I'm having sore throat. Sorry about it. Okay, thank you very much.
Okay, sir. Okay, sir. Thank you so much, sir.
Thank you, sir.
Thank you.
Okay, now I end the session. Okay, sir. ठीक है, sir.
Okay, thank you very much.